So it's my pleasure now to start off the Integrated Energy System panel, which will give us some more of the what's really going on in Minnesota right now perspective. And we are very lucky to have as our moderator Nina Axelson from Evergreen Energy and St. Paul District Energy. Nina is the Vice President of Public Relations for Evergreen Energy and oversees public affairs for that company and its affiliates. Her role includes community energy planning and authoring studies, including reports to the Department of Energy and the International Energy Agency. Her work also features education programming, and she will do a wonderful job introducing our panelists. With that, I'll turn it over to you.
Thank you, Ellen. All right, I'm going to try and see where this mic is going to have a magic spot here. So really pleased to be joining the group. I'll offer that I missed a little bit of the morning, so if anything I say happens to be out of context, I hope you accept my apology. But it's amazing to walk in just a little late and have everybody coming out of the room have such great energy, sorry for the pun there, but really having people excited about the conversations already this morning, the points that are being made today. And I think for those of you who I've known for years, to already have comments being made about 3 or 4 years ago, the same people wouldn't be in the room, the same people wouldn't be talking about this. It's clear that we are on this wave of change, and it's really great that there's so much commitment to it, there's so much creativity going into it, that we are all ready to talk about how our systems are changing and recognize the potential of all those things. So for us, for those of you who don't know us, we have a multifaceted organization that operates as a utility. That's how you know us as District Energy St. Paul, but also community energy planning, operation of systems such as the Duluth Energy Systems in Duluth, Minnesota. So we get to see this from quite a few different perspectives. We purchase energy from some of the folks at this table. We sell energy to some of the folks at this table. We've done energy planning with folks at this table. In general, I think you guys are great. So it's really about these partnerships that are changing quite a bit. And I think one of the things I just wanted to illustrate with that is there's a partnership and an intellectual exchange that happens with this, but it also really illustrates that anything that we're doing with energy solutions has to be cross-jurisdictional. It has to be crossing different sectors. So for years, everybody thought of us as a thermal company. We sell hot water and chilled water. We've sold steam. We're the thermal guys. And if you were in a room with us, you'd hear us say, what about thermal? What about thermal storage? And now it's so much more common for us to understand that that's just an integrated part of what we're doing. So in downtown St. Paul, we're doing combined heat and power. This is not two very separate plants. This is not two separate industries. The efficiency of it is all baked into the fact that we can do more renewable and do it more efficiently because we understand the two byproducts of that process. So right there is our first and most long-standing example that's been around and has shown how effective it is. But there's other newer examples of where we're doing this. So we're working with quite a very diverse partnership in Prospect North, or Prospect Park, Minneapolis, on the University Avenue District project. And it's a very small scale project. First phase will probably be 4 to 5 buildings. But we've been working on it for 2.5 years, and now the solutions that are coming through are to use energy recovery off a wastewater system, so just a municipal sewer system, or the Met Council's sewer system. There's this great opportunity to take that, and you are going to have a much lower greenhouse gas emission profile, about 20%, by using that solution. It's cost competitive with the lowest cost solution for that neighborhood. 20% is great, but if you integrate thermal storage, it jumps to 40% savings on greenhouse gas emissions. So, and it's not that we are changing how much energy we're directly taking from the wastewater. It's about the fact that it's a variable resource, just like some of the other resources we talk about on the power side. But to be able to do that and to be able to use that source and not have a fossil fuel backup to it, you really do need to integrate storage. So again, thinking about it on the thermal side, but for the most part, the building load can affect both thermal and electric. So I just wanted to make those simple comments because I think it's really important that these conversations keep happening. I'm so thankful to the University of Minnesota and Ellen for putting these ideas forward, but that we keep talking about things across the different sectors, that we talk about them across the different technologies. There is no one solution that is going to be, we figured it out here, because if you just figure it out here, you really haven't figured it out. So that's my little evangelical moment for the day. With that, I have the pleasure of making some introductions and forgetting my cheat sheet. So first we'll hear from Al Choi, who is the manager of Xcel Energy's Emerging Technology Research and Development Team. So he'll be up first to set the bar for everyone. Then we'll hear with Jeff Haas with Great River Energy. He is the Energy Efficiency Program Coordinator with Great River Energy's Membership and Energy Markets Division. I'd like to see that on your business card. That is amazing. And then Julie Pierce with Minnesota Power, who is their Director of Power Supply, and Seth Mullendor, yes, Project Manager for the Clean Energy Group. What a great, diverse panel, and we'll have Al come up and get us started. I should remind that the cards are available, and please do submit those so that we can have a really robust conversation when the presentations wrap up.
All right, great. As Dr. Ned Mohan mentioned earlier, Xcel Energy has been exploring battery energy storage since 2008 with that wind to battery project. What I'm going to talk about today is our solar plus battery storage projects that we've recently been conducting. And I'll make an exec summary first real quick, and then you can choose to tune out the rest of my presentation if you'd like. So here goes. Xcel Energy, 2 battery storage projects, one big, one small. In summary, batteries work, batteries are expensive, and we still need to understand more about stacking the values and understanding how to optimize them on our system. So if you want to learn more, stay tuned. Our battery projects are located at our SolarTAC facility in Aurora, Colorado, just near our Denver International Airport. The big battery project we call Solar to Battery. It's a 1.5 megawatt, 1 megawatt hour advanced lead acid battery. Think of it as glorified car batteries stacked inside this big container. There's 1,200 of them, and it was tied to about almost 800 kilowatts of concentrated solar from an adjacent dual-axis tracking farm next door to it with Amonix solar arrays. Adjacent to that battery project, we have a smaller one. It's a 25 kilowatt, 50 kilowatt hour system, so a 2-hour battery. Neighborhood size, as we like to call it. The unit's about the size of a big refrigerator. And its chemistry is a sodium nickel chloride, so it is molten salt. And the way we're testing that is by creating a simulated neighborhood of 4 homes. These homes average from, let's say, a 1,500, 2,000 square foot home all the way up to a mansion size, 5,000 square foot home generating 7.5, 8, 9, 10 kilowatts, depending on how we load up the system. So the red dot there kind of shows you the overall look of the facility and where our projects are located. I promise there's a lot of pictures here, so that's coming up. But essentially, how we test these batteries, we're looking at the fundamental characteristics of these batteries. So you'll hear terms like smoothing, ramp rate limiting, time shifting, voltage, reactive power support, and of course the sizing. A lot of technical terms here. For those of you who don't speak battery geek, smoothing, think of it like, you're driving down a road with your car and it's a real bumpy road. Your shock absorbers sit there within a band and trying to keep your car ride smooth. That's what I think of solar as the intermittent solar. It's the battery's trying to make that output smooth within a certain range. However, if you hit a huge pothole or you're coming up a big hill or going down a big hill, your gas pedal or your brake act as the ramp rate limiting for the large changes in scale of solar. Time shifting, a lot of folks are pretty familiar with that. Save now, use later. And then reactive power support and voltage support, essentially making sure that everything stays within the parameters so your light bulbs don't explode and smoke doesn't start coming out of your valuable electronics. And then battery sizing. Want to make sure that you're putting the right size battery out there and investing properly. If you're going to be using for regulation, you're going to size it one way and use a certain chemistry. If you use it for time shifting, you're going to try to size it and another way for a greater depth of discharge. They work, as I mentioned. Essentially, we've completed our solar battery operations. We should have a final report coming up here at the end of the year through EPRI. By the way, our partners for both of these are EPRI. The CES, Community Energy Storage Battery, that'll be done towards the end of next year in 2016. Promise some pictures. So Here we go. Here's the big battery getting loaded up on the trailer. These are decommissioning pictures, by the way. These are what the 1,200 cells look like. That's actually 600 right there, and then another 600 on the other side. Battery maintenance program should actually be called a battery fitness program, because when you have to lift them, they're about 60 pounds each. Our community energy storage pilot, as I mentioned, it's about the size of a refrigerator. The PCS from S&C is right next to it, and it is tied into those 4 simulated homes that I talked about earlier. And you can see those the solar arrays there. The 2 taller boxes you see over there are the resistive and reactive load banks. These guys simulate the loads inside larger scale homes. Behind that are 2 smaller resistive-only load banks we call our easy bake ovens. Essentially, they're heat loads, and they simulate the loads in perhaps a smaller home. So what have we learned thus far? When we talk about it from a demonstration perspective, you really think about batteries as kind of like a relationship. They're not turnkey integration. You just can't plop it in the ground, turn it on, and go. Everything's site-specific, circumstance-specific as well. Hey, chemistry matters. If you're going to use a battery for, let's say, regulation, advanced lead acid works great. It's very power intensive. However, if you're going to try to discharge that, as we have, to a very low state of charge, it does not work very well. Lithium ion or some molten salts may work better. And then lastly, you got to communicate. And they're heading towards better standards right now with their power control systems using DNP over 81650, et cetera. But this is still something that needs to get worked out, and it's always a little bit more specific by utility and by the operation needed as well. So from a research perspective, taking a step further from the operational sides of things, what we're learning is that if you're going to really maximize the use of an energy storage, battery energy storage system, you got to start stacking values. If all you're doing is buying it for time shifting, it's going to take a while for you to make your money back. However, if you can do time shifting plus voltage support, plus smoothing, ramping, and then even throw it into the market if your area allows, you'll recover a lot faster. You've heard it already from numerous folks before. The policies are changing, and it's driving new battery markets. For example, PJM, I kind of think that, that kind of market was created just for their use. And in doing so, it's helped the recovery of those batteries much faster. And then the cost of batteries have to come down, as I mentioned. Right now, you're looking at installed costs as low as $600, which is a lot better than it was when we first stood up our battery projects, but they still go up to $1,300 per kilowatt hour. So we need to keep looking at the cost of batteries as they go down. So wrapping this up here, what's next? Our CES pilot, we're going to continue operating it and analyzing it through the end of this year, and then we'll have our final write-ups through EPRI at the end of next year. SolarTech 2.0 is undergoing some revision thinking right now, going beyond just a solar research technology center, and looking at how we may expand that to other capabilities, microgrids, distributed energy resource management, et cetera. And then lastly, in general for Xcel Energy, battery economics, making sure that it's a cost-effective means is key. And lastly, making sure that we optimize all the value and operations of the battery on our grids. So, hope you all stayed awake during that. Thank you very much.
Thank you, Al. I'm sure nobody could have dozed even for a moment. That was very well done and very concise. So we're going to have Jeff come up next, and just a reminder that if you want to learn a little bit more about all these folks, their bios are in the program, but I think it'd be more fun to bombard them after the session if you don't get a chance to ask them a question during. So take it away, Jeff.
Thanks. Well, good morning. This is about the only time that I'm given the latitude to get myself in hot water during a presentation. So with that, I've provided, all of you should have a brief handout which just goes into some more detail of our electric thermal storage water heating program, which is a program that's been around for Great River Energy for a little over 30 years. It's a program that grew somewhat out of necessity as we entered the 1980s recession. We had a brand new power plant, and it wasn't the MISO market, so we had to really try to find opportunities to fill in those valleys at the nighttime hours. And electric thermal storage, water heating, kind of grew to become a resource that helped us manage our own loads over that time. And just by way of some background information, ETS, as we call it, is a large capacity water heater that provides us the ability to provide a household's entire domestic hot water needs during a period from 11 p.m. to 7 a.m. So basically shifting a major end use of an individual household entirely to the off-peak hours. And over time, this resource has really grown into a 65,000 points of energy storage throughout our system. And really it serves as, kind of a hot water chemical battery, as we call it. It's not, we're not putting electricity in and getting electricity out, we're putting electricity in and getting hot water out, which every household needs, and has a fairly predictable consumption pattern, from one day to the next. So yeah, this is just kind of an example of how our load curve looks with those ETS charging periods overlaid on it. And you'll see this was last weekend, and we had some load control going on during that second night. And that kind of shows the example of our other load control programs, which are separate and distinct from the ETS load control program, which is really something that is built in and operates on a daily basis, 11 to 7. It's a program that's operated with, right now, radio frequency control. So it's a one-way communication device. And currently, that total resource is giving us the ability to move upwards of 300 gigawatt hours annually into those off-peak periods of time. And over the evolution of this program, it's starting to show higher value as we've moved to variable generation resources such as wind, and definitely as we've moved into the MISO market. And that value is really demonstrated here, where the MISO market, the dash line up here is really the price, the wholesale price of power. And so the main value stream that we saw going into this was trying to take advantage of that low-cost power during the off-peak hours. Just so happens that that's when the bulk of the wind energy on the MISO system is coming online. And so it's also providing this ability to absorb some wind energy through that system. And we're looking at it as evolving to the next phase, which is adding this grid interaction. And so the idea being that as long as that household has hot water, it doesn't matter what you do to it overnight. You can move it up and down, you can play with it, as long as that main promise of we're always going to have hot water for you is met. And if you don't meet it, you find out about it pretty quickly. What Al mentioned, kind of this bumpy road that we're working with, and so that electric demand that I showed you earlier just doesn't follow a nice smooth line. There's a lot of balancing that goes on with respect to the change in supply and demand. And one of the items that GRE has been pursuing over the last several years is trying to incorporate more control, interactive control, two-way control on this ETS resource that allows us to not only turn it on and off, but also to potentially vary the wattages in those elements. And so if you can kind of do this immediately with a low latency period between your communications network and those end-use water heaters, you can really closely follow the variability within the market. And in doing so, you might be able to take advantage of other grid resources or grid values and potentially get paid for that. In one of the documents you've been given, there's a graph of cost of various storage technologies. And one of the big benefits of ETS storage is that it's a very low cost, and that low cost can be met partly because a household needs a water heater. So if you're entering into an agreement with a household, they're buying a water heater, we're providing a low-cost rate for that. In exchange for that controllability, that cost is really being partly shared by the utility and the household. This is an example of what could be a situation where not only is a water heating being optimized to low-cost power, but also being potentially paid for ancillary services that could be provided in the market. The idea being that if you could do that in a way that the market lined up, you could almost turn these things into a revenue producer. That's a very, very promising thing that we're looking at and trying to pursue, and really looking at new technologies that kind of, along the lines of the Internet of Things. Is there a controller that we can put together that would connect to a household's Wi-Fi system and bring that variability and that ability to change very granularly into our market dynamics, and then begin to participate in a way that is very much a two-way system, again, as long as we're delivering that hot water in the morning. So thank you, and I look forward to any questions.
Thank you, Jeff. Clearly, you guys are getting some great stuff out there because the questions are streaming in. As we get Julie prepared to come up, I just want to make sure she's aware that she has to beat out the current jokes, one for battery fitness and the second for being in hot water. So that's the bar that's been set for battery storage humor. All right, so Julie, all yours.
Well, thanks, Nina. Lucky for me, I'm not going to talk about battery storage. I'm going to talk about hydro storage, so maybe I get off the hook on the joke. Okay, yes. Good. Well, I'm kind of a different topic here from what we've had, but I'm really excited to be able to talk with you about some unique things that Minnesota Power is doing to leverage our system as a whole for storage capability and optimizing renewable resources for our customers. And so my topic is a little bit different. Hopefully you can see the value of the energy storage that we're talking about here in our power supply portfolio. Did I get hit? I'm sorry. Down. So just a little bit about Minnesota Power. We are nestled up in northeast Minnesota. We've been around for about 100 years, and we've had a very rich history of energy storage. And we're also part of a larger organization called Elite. So I just wanted to kind of share with you kind of our footprint and where we serve our electric customers, about 144,000 customers up there, 24 hours a day, 7 days a week. I mentioned our history. So 100 years ago, about the time that people were saying that intermittent resources and storage was on the cusp of being needed, and we've been developing ever since, Minnesota Power was the largest hydroelectric utility in the state of Minnesota, and we still are the largest hydroelectric utility. And our largest resource is our Thompson Hydro Reservoir. And this is an energy storage, a hydro energy storage system that we've had for, like I mentioned, about 100 years, and an 80 megawatt storage unit up in northeast Minnesota. Very visible from Jay Cook State Park if you ever get the opportunity to visit. It's a beautiful recreation area, as well as a very productive hydroelectric dam for our customers. That reservoir system allows us to really store energy from hydroelectric source and utilize it and optimize it for our customers. So I just wanted to call out our long history of hydro and then this really large reservoir that's available to us to store energy that naturally occurs through hydro right here in the state. But really the crux of the new thing that's on the horizon for Minnesota Power customers and really the region is leveraging some infrastructure, both man-made and natural, that we are able to get at with our geographic position with Canada. So we love our neighbors to the north. We've been partnering with them for decades, and this latest installation of partnership really has a lot of unique traits that allow renewable energy to be optimized. And Mr. Tong talked about how our system is very integrated, and power flows from, here all the way to New York and back, and we need to be able to leverage our geographic resources that are there, wind in the west, hydro to the north, solar to the south, to be able to really get ourselves the most optimized power supply and renewable power supply possible. Our partnership with Manitoba starts with some existing infrastructure, and that is our large wind build out in North Dakota. So we build some very high-performing, efficient North Dakota wind from 2007 to now. So we have 500 megawatts of wind out there in the west, indicated there by the arrow in North Dakota. That wind is a really great resource, operating at capacity factors above 45%, and we're very excited about that efficiency of the wind. However, it's still not 100% of the time, and it's still not getting that full capacity resource and availability that we would like. So we went on a mission to identify how can we leverage that resource and take the wind that's blowing when our customers don't need it, store it, and bring it back when they do need it. And by looking at the large-scale nature of our wind development, we identified Manitoba Hydro and their big hydro reservoirs up in the Nelson River to be able to be a nice partnership opportunity. So through the development of lots of wind in North Dakota, Manitoba Hydro is building a very large hydroelectric dam up on the Nelson River, which is a natural reservoired river. They're able to store energy in their vast hydro system up there, which I have a picture here just a little bit later. And it allows us to be able to store our wind that we might not need for customer needs in the off-peak hours, and then bring it back to our customers in the on-peak hours when it is needed. And this is facilitated through the creation of a transmission line, a new transmission line from Minnesota to Canada called the Great Northern Transmission Line, which is set to start construction in 2016. So again, we call it the natural battery, inherent to the geographic location of our state, and really leveraging resources from the north and wind from the west to optimize renewable implementation in the Midwest. And then I just included a picture of the hydroelectric resource in Manitoba Hydro. We really like to think about optimizing resources, and the strength of Manitoba is their hydro system. You see all the blue there. The connection with Hudson Bay, its ability to store energy throughout that whole system is phenomenal. And being able to just tap some of that value for our customers as we try to store wind was a natural synergy and a very low-cost option for our customers when compared to alternatives. So our partnership with them will start in 2020, and we see, as with all interactions with Manitoba Hydro, I'm sure that will go on for another 100 years as they've been interacting with the state of Minnesota and our energy needs. And that is what I had today.
Thanks, Julie. That's great. I was really looking forward to some diverse ideas and diverse opinions and technologies on this group, and so far, so good. So bring up Seth to round everything out. And so last chance to really start funneling any questions left, although we have a pretty good supply here. But I think it's going to be a good Q&A after Seth here.
Okay, thanks, and hello everyone. I'm from Clean Energy Group, and I'm actually based in Vermont, so not Minnesota. For those of you that aren't familiar with our organization, we are a clean energy advocacy think tank. We promote financing and clean energy technologies in a number of different sectors across the nation, supported by foundations. And we also manage the Clean Energy States Alliance, which is an alliance of state financial institutions and other entities within the states that are promoting clean energy. So I'm going to bring things back around again to solar and storage, like Al talked about. And I'm going to talk about something that often isn't valued when we're talking about energy storage, and that is resiliency. And so first off, what are we talking about when we're talking about resiliency? We're talking about what Dr. Mohan was saying, avoiding the freezing in the dark problem that you have with renewable energy. And resilient power is not just backup power, though. It's power that can provide a benefit year-round, not just when the main grid is not available, but throughout the year. It can provide both value in helping with renewables integration and other grid services that something like a backup generator is not so well attuned to provide. In addition, it also can provide economic resiliency for the facility where it's sited. This can be in a number of different ways, reducing customer bills or providing grid services that can provide certain revenue streams. So let me show you what we're talking about here. So first of all, what's the problem with just having solar only? This is basic, really simple depiction of what a solar system looks like. The problem is, and the problem that people have found that have had solar, is the grid-tied inverter. I come from the Northeast, and that's where a lot of resiliency action is taking place because of Hurricane Sandy. And when Hurricane Sandy hit, a lot of people with solar power, with solar panels, thought they'd be fine, found out their systems did not work because they're tied to the grid, and you can't have power fed back into the grid when there are outages because there are workers out there trying to restore power and people might get hurt. So what you need is an inverter that's going to detach itself from the main grid and island itself during times when the main grid isn't there and insulate a system so it can become kind of its own microgrid. Most of the systems out there, solar systems, do not have that kind of inverter. They are starting to be developed. They are out there commercially now, but very few of the systems that have solar have that kind of inverter. So what happens when you add storage to the system? There are a couple of ways to do this. This is a DC tied system. You can also have AC, where you have an inverter for the solar system and you have a separate inverter for the battery. This is a DC tied system where all the flows go through one inverter. It's a dual inverter where energy can flow both ways. The solar panels can directly charge the energy storage, or they can flow through to your load panel to the home, or it can flow to the grid if you're producing more energy than the facility needs. I should also say that the kind of system I'm talking about is mainly behind the meter systems, customer sided. You can also have solar and storage at the utility level, providing power at substations. There are a number of projects in development or currently being tested out there that are at the higher utility level, but my talk is mainly about behind the meter, sited at a customer facility. So the battery-based inverter is one change. The other change is this critical load subpanel. The critical load subpanel takes the loads that you want to support through your solar and storage system when the grid is unavailable. That top part, the central grid, utility meter, main circuit panel, when the grid's not there, all of that gets disconnected from the system tied into the facility. Everything else continues to work the way that it was working before. Why do you need the critical load subpanel? Why can't you just put it all through the main circuit panel? Part of that is because of some of the realities of the limitations of energy storage at this time. It's not economically viable in most situations to power your whole facility with energy storage and solar. It's mainly because of the cost of batteries. So we've heard before that batteries are not great with their power density. They are great at, they're much better with their energy density. So some of the high-powered technologies that you're using, some of the motors starting up, things like that, energy storage may not be the best at supporting some of those loads. You might need other systems to go along with it. And you can easily tie in existing generators, things that a facility already has, into these systems. We've also found that micro CHP, small heat and power units, are good for facilities as well to provide extra power for some of these more power-inducive loads that you need to support. Whereas energy storage is great for communications, outlets, lighting, water pumps, things on that level. So again, this is resilient power, what we're talking about. The grid is off, you can still support some of your critical loads, the facility islands, and it keeps some things going. Not everything, but a lot of things. It can also be used by, in commercial facilities. They can address demand charges with this. When you have dynamic rates, you can use some energy arbitrage to use energy from your storage when energy prices are high, and you can pull from the grid when energy prices are low. there's a number of different value streams, and we're going to get into a lot of that later on today, so I'm not going to get into all that now. But as many people have said, to pay for these more expensive systems, you need a lot of value streams and a lot of savings streams, and you need to be able to stack those to make these systems pay off. But the benefit of resiliency is one thing that is often not factored in because there is no market price for resiliency. And it's dependent on each facility and each individual person when you're talking about on the residential side. So just to wrap things up, I want to talk about a few different projects. These are two projects that Clean Energy Group has been involved with, and they're two very different projects. The top one is the Stafford Hill Solar Farm, and this is in Rutland, Vermont. This is 2 megawatts of solar panels, and it's tied to 4 megawatts of storage. Half of that is lithium ion, half of that is lead acid, and they're there for different purposes. This project is done through Green Mountain Power, which is a utility in Vermont, and is funded in a large part through the Department of Energy. The system also provides backup power, resilient power for a local high school, Rutland High School, which is used as an emergency shelter for the town of Rutland, which faces a lot of power outages due to severe storms and a lot of winter storms that hit the area. The bottom one is a project that's still in development. This is actually in New York City. This is a low-income affordable housing project that is called Via Verde. And this is going to have a much smaller system. It's going to have a 60 kilowatt, 90 kilowatt hour battery, and that's along with a micro CHP unit. And it's mainly there to support water pumps so that when the grid is unavailable, people who live above the second floor can have access to water. A lot of people in these buildings, they can't get down the stairs. The elevators may not work when the grid is down, and they need to be able to have access to clean water for their families. This is a system that we're still waiting for the New York Fire Department to give the okay on being able to put lithium-ion batteries in a building, which is a problem in New York City. Not in a lot of the other areas in the U.S., but it's a problem there. But we expect the project to move forward next year. And the energy storage side of this actually has a payback of 8 years. And that's due just from reducing the demand charges that the commercial part of the building has. That's the common areas, that's the common resources in the building. So just from reducing demand charge payments, this project is expected to pay off in 8 years on the energy storage side. The solar side of it will have a 10-year payback. So storage is looking even better than that. Wanted to just briefly mention another project, and that's right here in Minnesota. There's a project in Duluth that a nonprofit, Equilibrium 3, is working with Minnesota Power on. They are currently looking at getting some funding to put a battery in a university, I think about a megawatt battery there, and support a fire station too with a smaller battery. So that's a project we're working on right here in Minnesota. It's solar and storage. Minnesota is not always known for their storage or their solar potential, but you can do it right here. And in much of the Northeast, which has a similar potential for solar, these same projects are being done. So that's all I have for you. Thanks.
Fantastic, Seth. Thanks for giving us, again, another perspective of scale and integration. And thanks to the audience. You guys are going to make me look really smart reading off these questions, hopefully. So I want to start with some clarifying questions. One, because the panel did such a good job of staying on time, we're going to start with some easy stuff here, hopefully. And then also just to make sure we're clear on the concepts. So Seth, one came in for you, just to talk briefly about how the lead acid and lithium-ion batteries are actually interacting in the Rutland system. Could you just clarify that briefly?
That's a good question, and let's tell you the truth, I'm not entirely familiar with how the two technologies are being used. The project is getting commissioned this month. From what I understand, the two technologies are there for different purposes. The lithium ion is there for frequency regulation and smoothing of some of the solar, whereas the lead acid is meant to do some of the more long duration resiliency side and for more extended power outages to provide power for that. So it's more the lithium ion for the frequent cycling that's going to be done and the drawdown of discharge. And the lead acid there is for more sustained power throughout a longer duration.
Thank you, Seth. So I'm going to turn to Julie next. Actually, kind of a two-part logistics clarification. Transmission line below or above ground?
Yeah, the transmission line is above ground. It's a large 500 kV transmission line from basically Duluth, Minnesota, up to Winnipeg, Manitoba.
And then could you speak just a little bit more about the transition from the wind generated to actually the agreement with Manitoba Hydro? How is the wind transferring over to the storage, just from a technical standpoint?
Yeah, so from a technical standpoint, what the agreement allows is for Minnesota Power to utilize Manitoba Hydro's system to store its wind. And so essentially, our wind is generated, and when we deem that we do not need it,
Thank you.
When we don't need it for our customers, we're able to send a portion of that up to Manitoba Hydro's vast reservoir system, store it there, and then bring it back when our customers do need it, mostly when it's most cost effective for them, which is on peak time. So the agreement allows us to do that activity between the two organizations.
Very helpful. Yeah, thank you. All right, Jeff, you're up next. So could you talk just a little bit more about the installation at the home level and total equipment cost to install?
Sure. The installation at the home level is one of the key, I think, challenges. If you're moving into a house, you do need a 240 volt circuit. Whether or not that basement is finished or not will dictate the cost of the installation. But the ETS, the thermal storage water heaters themselves cost right around $1,000. There's been some changes in the market that is pushing that price up. And we might be looking at $1,500 now for some of those units. Then the radio frequency, the control receiver itself is another approximately $100. And so when we're evaluating technologies that might replace that radio controller, we need that to come in at a price that's definitely below $300. And then whatever the associated cost of installation are related to the electrical side is something that might vary. But for the most part, a lot of these water heaters come with pretty long warranties. The Marathon water heater, formerly produced down in Eagan, Minnesota, is now in Alabama is where they're making that. Had a lifetime warranty on their residential products, so it was really a buy it once, and it's going to take care of itself.
Great. I bet you saw this coming, Al. So let's talk just a little bit about your batteries. So life cycle expectation on the battery right now?
So on our large battery, which was decommissioned last year, we didn't look at it so much in number of cycles itself because the way we exercised the battery was really outside the norm. Mm-hmm. But the company, when we had signed on, was looking at about a 10-year lifespan of the battery itself, and the depth of discharge really determines how long the battery is going to last. So every application you have discharges the battery differently, different speeds, so that one wasn't really looked at in terms of that. Also the same, we don't operate normally with looking at number of cycles. We look at it in the usage of the battery in terms of its various functions. So to try to quantify it, we'd only have to look at doing time shifting and then say we're only doing time shifting X number of times, and that's the number of cycles of the battery itself. But we're looking at it more towards the operation of the battery itself and seeing how it performs throughout the 10 to 15-year life cycle that they tell.
That seems like a robust way to analyze things. So now we're going to open it up a little bit more to the group here. So everybody's projects are a little bit different. I'm wondering if each of you could share the top 2 to 3 drivers or benefits that are motivating your organizations to do this work. I think it'd help for the conversation here of, why are we doing this, and how, so the rest of us know how we get behind it.
Sure, I can start. We've looked at, as I mentioned, battery energy storage since 2008, and we saw the opportunities come up with our large battery and small battery to understand and kind of get ahead of the curve, if you will, about solving, well, I'll call it the solar problem, right? You have the introduction of high penetrations of solar, just like high penetrations of wind and the variability behind it. You want to understand and get ahead of how you can best integrate battery energy storage with your grid. It's a little bit different between reading how to fish versus actually going out there and learning how to fish itself. And we looked at these two opportunities as a great way to understand that. Because, you know, if you think about solar, solar has no inertia. It can go from 0 to 0 in no time. And given that versus wind, which has a ramp down, ramp up over several minutes usually, we have different circumstances on the distribution grid where a lot of solar resides, and understanding how we can mitigate a lot of the effects that come up from that.
For GRE, you know, this the electric thermal storage program is something that's almost part of the culture now of not only GRE but our co-op members. And we're predominantly a residential system. It's about, you know, it's 60% of our, you know, total energy sales are have residential members at the end of it. And residential is really driving our peak. We heard earlier that residential system, air conditioning really drives peaks. Electric water heating can also drive that peak as well. And so our impetus is really moving it off of that peak, you know, system impact. And now, you know, given the evolution of technology and the ability to now have, you know, this interaction with the wholesale market, our interest is really continue to use this resource to drive value to our members. You know, over the last 5 years, we've been working, you know, with the Department of Energy and other stakeholders because of some efficiency standards that went in place that were proposed in 2010 and took place actually this year, that effectively eliminated the manufacture of these large capacity units. And thanks in large part to, you know, our congressional delegation and Senator Klobuchar and Senator Franken, we were able to get some legislation passed that allows this resource to continue to be utilized. You know, it's the next generation water heaters of this size is really going to be something that has to be unlocked through a utility demand response program or ETS program, and really with an eye towards, you know, how this grid interaction and grid enabled water heater will really evolve around. And so we're excited about not only the promise of being able to continue to do this and take advantage of it, but to continue to use it as an integration with our system.
How about you, Julie?
So for us, it really is driven by our power supply strategy. Right now, and since the early 2000s, we've been really in a transformative mode with our power supply. And our current energy-forward power supply strategy has really identified moving our generation mix and our portfolio to a much more balanced mix of renewables, natural gas, and coal. And we think a more diverse, balanced approach to power supply in the future is going to better serve our customers. And this Manitoba Hydro synergy and partnership is really a pillar of that strategy. And the reason why it's so good for customers and so good for the region is really about our customer mix in the Northeast, as well as the overall region's need for more renewable energy. And the actions that we're taking for getting this transmission line in place and having this storage available of our wind and making our wind more optimal and more efficient is going to set us up for decades to come. Our customer mix, you might say, well, why do you need this much and why so big? Our customer mix is much different than the rest of the states. Instead of a 50-50 mix, we have large industrials that make up 70% of our customer mix. That means they're very energy intensive customers that need power that's very reliable and economical. So with a 70% industrial mix, and looking at the scale of the power they need 24 hours a day, this opportunity to optimize our utility scale wind with utility scale hydro reserves in the north is very cost effective when compared to other storage opportunities we have. And really it's about optimizing in partnerships, and that's something that I think this state has done so well. We've had several partnerships around this table and in this audience to find unique and creative ways to implement power supply options in the state. And this one really leverages and optimizes infrastructure, our geography, and those partnership capabilities.
Seth, anything you'd add?
So at Clean Energy Group, I mainly work on our resilient power project, and really the main motivation behind that project is the fact that diesel generators suck. They're terrible. They pollute, they're loud, and in a large part they're unreliable. And this is the main source of backup power that we have in this country. It's what all the codes are written around. By some estimates, in Hurricane Sandy, 60% of diesel generators failed. 2 major hospitals I know have had to be evacuated, and this hit the low-income, vulnerable communities the most. So our project is trying to, in particular, bring these new, better technologies to the communities that can least afford them and can least afford to not have this power resiliency.
I think you guys are the most Twitter-worthy panel. You have very deep comments, but also some great sound bites here. Diesel generators suck. Maybe that's a good reason to bring up our next comment here. So I think I look around the room and know there have been people that have been very patient as the utility world has been transforming, and we know a lot of things don't happen overnight. However, moving from research and development, moving from demonstration project to greater rollout is critical for any of this to work. So can anybody comment on where you see the tipping point? Is it based on a percentage of wind and solar on the grid? Is it based on something else? Where's the tipping point for your organization to move from demonstration to rollout, deployment?
Yes.
Of course.
All of the above. It comes down to cost, at least from our perspective when we run these projects. So our projects as demonstrations are obviously looking at it from a different perspective, understanding the operational aspects of it, and then taking our learnings and then translating them into a value going forward. But as I mentioned earlier, battery energy storage right now is still very expensive. So if you were trying to implement that as a way of relieving transmission or distribution congestion right now, there are probably more cost-effective ways to do that. But again, this is not my area, so policy and regulation, that's going to help drive a lot of the changes going on. And I know there's a panel on that this afternoon, so I'm going to defer to them on that one.
I heard that as a punt. Okay. Jeff?
I offer that I think our system is fairly well along. You know, where we're going now in terms of this interaction with the grid is really a question of value associated with the ancillary services market and whether or not that function is appropriately compensated within the wholesale market and how that function exists. We kind of talk about PJM and MISO as kind of well, this is the wholesale market here, and this is the wholesale market here. In reality, there's very different market constructs that exist in each of those, and to a large degree, they can drive that behavior that we talked about. But it's the behavior of utilities and what they do from the standpoint of providing these other services to that market, and so I think that question of, well, how much incremental value does GRE or any utility get from not only shifting the water heater load to the nighttime hours, which you could argue is the bulk of it. If you're going to look for low-cost power, that's where it happens, and it's pretty reliable year over year. Whether or not that value associated with the variability and the ability to have two-way communication is worth that investment is going to be a question of the market, and like Hal, I would punt as well to that next panel.
As long as you're not punting directly to Julie, because I think she might.
I think for us, for Minnesota Power, again, our conversations with our customers right now in all sectors is about cost. And so we really enjoy some very affordable electricity in the state of Minnesota as we compare ourselves to other states across the U.S. And I think the important part is them knowing what their options are, the value of those options, and how they can be applied. And really, at the end of the day, we are serving our customers and what they need. And if they want additional options for storage, for renewable, for others, that is part of what we are there to serve. And so through the partnerships, the demonstration projects, the funding of research, as we do with the U of M, identifying other options to do storage in unique ways, I think that's how we get there and get over the tipping point. But it really does come down to cost. A lot of the cost models right now that we heard today are not tipping the scales for customers to have that large scale demand. But we're close, and we see projections into the future where energy prices are going up. They're not necessarily going down, and so all of these applications are going to be very relevant very soon. And I know that as utilities, we're here and ready to help integrate any way we can.
Okay, like everybody else, yeah, cost is important, but I'm not worried about, I mean, I'm talking about batteries, I'm not worried about battery costs. They're coming down, and there's enough competition that's going to keep coming down. Tesla has already quoted some very impressive price points, and we'll see if they can deliver on that or not. And some of the projects that we're working on, stuff in PJM, stuff in New York where there's high demand charges, these projects already pencil out, and they already do pay for themselves. So what's going to happen is we're going to have to figure out how to make these markets, how to get the markets structured properly to properly value all of the benefits of storage. Because right now, even in these places where they are paying off, we're talking about one value, maybe two values that storage provides. There are a number of them that certainly they have no market out there right now for them. They're not being paid for the services that they can provide. So once these markets get figured out, then it's going to take care of itself.
That's great. So I've been given the red card. I think in soccer that means something totally different, but this means that we're almost breaking for lunch. I want to thank the panel, but I think the conclusions for me here is the same thing I've been hearing in all the years I've been in the industry is nobody answered a question and said, well, the technology is just not there. We've got great minds with great solutions that are putting these things forward. Now, I mean, there are some specific things of maybe this solution doesn't work for this application, and so it's really about suiting those things together. But I think it's the charge of the group in the room, if we're going to punt not just to the other panel, but back to everybody here, of what are we doing to influence market mechanisms? What are we doing to be consistent at a regulatory level? I would say one thing that we certainly observe is we have to be very cautious not to just pick that one thing. There was 4 great approaches here and even deeper into their solutions, and if we were to all say, let's pick that one, make it the winner, and make sure we ride it into the sunset, that's not going to work for us. So let's make sure that we are very cognizant of that when we're representing all these diverse opportunities and how they work. Let them get into the market and have some competition. From a policy level, make sure that we're supporting a diverse approach. With that, I will let the people in the afternoon solve all the other things. But really great panel, great commentary. I think we should give them a good round of applause.